So there are two potential sources of hydronium ions in a solution that contains an acid. We've got the ionization of the acid itself. So our acid HA, that's going to react with water, produce hydronium ions, and the conjugate base. We also have the autoionization of water as a source of hydronium ions. The equilibrium constant for this is very small, but it does occur. So we need to recognize when can we ignore the autoionization of water and when do we have to pay attention to it. Well, we can ignore it when the source of hydronium, the acid source, is much higher in concentration than the autoionization of water. Then this is like the X is small approximation. It's so small that even though we know it's there, it doesn't matter. So where is that dividing line? It's approximately an acid concentration of 10 to the minus 5. So if we have, that's an extremely dilute solution, 0.00001 molar HCl or lower in concentration, then we have to consider the autoionization of water. Above that, we really don't, okay? So strong acids, again, by definition, strong acids ionize completely. How many strong acids are there? 6. Do you remember what they are? Yeah, there's hydrochloric, hydrobromic, hydroiodic, and nitric, sulfuric, and perchloric. Okay, 6 of them. You should memorize those. So when we're looking at a strong acid solution, the concentration of hydronium ion is same as the concentration of the strong acid. So if we have a 0.1 molar HCl solution, this is a strong acid, that ionizes completely, that'll give us 0.1 molar H plus or H3O plus and 0.1 molar chloride, right? It ionizes completely. So the hydronium ion concentration is equal to 0.10. And then the pH is the negative log of 0.10, which will give us 1.00 as our pH. Weak acids are a little more complicated because they are only partially ionized, and so it becomes an equilibrium problem. The initial hydronium ion concentration, we usually say is approximately 0. So here we've got an ICE table for the ionization of 0.1 molar weak acid. And we're going to say, we put in 0.1 molar of that, we're going to say that this hydronium ion concentration is approximately 0. We know it's actually 10 to the minus 7, but that's probably not going to matter. And this is 0, and then we look at the change, minus x, and plus x, and we get our equilibrium expressions, and then we can put that into the equilibrium constant expression. So let's do that for hydrofluoric acid. We've got a 0.25 molar hydrofluoric acid solution, and there's the Ka, 3.5 times 10 to the minus 4. So what I've got here is I've got my hydrofluoric acid, and that's going to ionize and form hydrogen ions and fluoride ions. This is our HA, there's our H, and there's our A. So initial concentrations, for the hydrofluoric acid, it's going to be 0.250 molar. And for the hydrogen ion, we're going to say it's approximately 0. Because 10 to the minus 7 is very small compared to 0.25. And the concentration of fluoride is 0 to start with. And we can look at the change. This reaction can only proceed in the forward direction because there's no products to go in the reverse. All the coefficients are 1, so this is going to have a change of minus x, plus x, and plus x. At equilibrium, we add the initial and the change, and so we get 0.250 minus x, x, and x. We're given the equilibrium constant for this, Ka. Ka is 3.5 times 10 to the minus 4. And that's going to be equal to hydrogen ion concentration times the fluoride ion concentration divided by the hydrofluoric acid concentration. So what I'm going to do is I'm going to substitute in my x terms. H plus is x, and F minus is x, and HF is 0.250 minus x. So that's the same as x squared over 0.250 minus x. So how do we find out what x is? Solver. That's what I would do. Could we use the x is small approximation? You can always try the x is small approximation, but then you have to check and see if it's going to work or not. I like my solver. So I'm going to stick that in here. So I've got 3.5 times 10 minus 4 on one side. And I've got x squared divided by the quantity, 0.25 minus x on the other side. And this is telling me that x is equal to 0.00918. Anybody else get that? Okay. And we look at that and we ask ourselves, well, is that a reasonable value? If we take 0.25 and subtract that, we're not going to get a negative number. So this isn't something that's out of bounds. So x then is the hydronium ion concentration, right? So this is equal to the hydronium ion concentration. We used the solver. Now that we know the true answer, we could look at that and determine whether x is small would be okay. We're looking to see if x is less than 5% of what it's being subtracted from. (3.67%). That's less than 5%, and so the x is small approximation would be fine here. Just for grins, let's do that. So I'm going to do x is small in blue. 3.5 times 10 to the minus 4 equals x squared over. And what the x is small approximation is saying is that x is small enough that when I subtract it from 0.25, it doesn't really change the 0.25, and so I can ignore it there. That, of course, makes the math much easier. And I get x is equal to 0.00935. So we play a little loose with significant figures here in Chem 1B. But at most, we should probably have 2 sig figs on these, right? Because of our Ka. And so this would round to 0.0094 molar. This one over here, we'd probably round to 0.0092 molar. Are those different? Yes. Is that difference significant? Probably not. Any questions? Do another one. Find the pH of a 0.0150 molar acetic acid solution. Here the Ka is 1.8 times 10 to the minus 5. Do we actually need to know the chemical formula for acetic acid? Not really, no. We can just say HA. And sometimes even when we know the formula and we care about the formula, it's tedious, and so we just write HA anyway. So let's just do HA. So here's our acid. It's in equilibrium with hydrogen ion and that conjugate base, which here would be acetate ion. Making a nice table. Initial concentration, 0.0150 for the acid. And we're going to say approximately 0 for the, the hydrogen ion. And 0 for the conjugate base. We look at the change. The acid's going to lose X. These products are going to gain X. And at equilibrium then, we have 0.0150 minus X, X, and X. Ka is 1.8 times 10 to the minus 5. And so that is the hydrogen ion concentration times the acetate ion concentration divided by the acid concentration. So that's X times X over 0.0150 minus X. Now, if we think about this one compared to the one we just did, is this more or less likely to be X is small approximation friendly? Less. The reason it's less is our Ka is smaller. That doesn't matter, but our initial concentration is smaller, 10 times smaller, right? The previous one, it was 0.25, and here it's 0.015. And so then whatever X ends up being is going to be larger in comparison. The previous one was almost 4%, and so that was kind of pushing the edge. This one's probably not going to work. So we can use the solver. 1.8 to the minus 5. Or 1.5 minus X. So I'm coming up with 0.00511. If I divide that by 0.015 and multiply by 100, 62%. Yeah, that's not going to work, right? So here we're going to say the hydronium ion concentration will be 0.000511. But what are we asked to find? The pH. So pH is the negative log 0.000511. And we're going to say that probably has two significant figures. I'm getting 3.29 for the pH. Any questions? Yeah.
So that you will solve the equation from Ka on top.
Mm-hmm.
It's always going to give you the hydrogen concentration.
No, it won't always. It depends on what your initial quantities are. If you're just starting with the acid and these are both 0, then it's going to work out that way, that X will always end up being the hydrogen ion concentration. If this wasn't 0, though, our hydrogen ion concentration would be something minus X. So we solve X, and then what X is comes from this line right here. Right? So X is the equilibrium concentration of hydrogen ion. It's the equilibrium concentration of A minus. And if we want the equilibrium concentration of HA, then we have to take 0.0150 and subtract X. Any questions? So here we have one labeled, finding the pH of a weak acid solution when X is small doesn't work. Now, again, we're going to do our ice table. Got HNO3 in equilibrium with H plus. Sorry, it's not NO3. That would be a strong acid. That wouldn't work. NO2. Initial 0.010 molar of the HNO2, approximately 0 for the hydrogen ion, and 0 for the nitrite. Change minus X plus X and plus X. It can be tempting to skip the ice table. I don't recommend that. It really helps you to see what's going on. So my Ka is 4.6 times 10 to the minus 4. And that's going to equal hydrogen ion concentration times nitrite concentration divided by the nitrous acid concentration. So in this problem, I'm sort of writing down the minimum of what you should show for work. Do you have to write out Ka equals H plus times NO2 minus divided by HNO2? No, you don't really have to do that. Do you need to write this out? Yes, you do. So it tells us that X is small doesn't work, so we're just going to go straight to the number solver. 4.6 times 10 to the minus 4. And these are, because these are all just a weak acid dissolving or ionizing, the form of this ends up being the same. And so when I go into my solver, actually all I'm having to change is this value over here and this one here, and the rest of it's all the same, which makes it really fast. So now I've got X is equal to 0.001927. If I divide that by 0.01, I get 19%. So X is small doesn't work with this one. So that X there equals our hydrogen ion concentration. That's what this column is telling us. This is our hydrogen ion concentration at equilibrium. questions asking for pH. .72 for the pH. On that previous problem, I realized I made a calculator mistake, and X is small actually did work on that one. Yeah. I just, when I did answer, I misunderstood what my calculator was telling me. Now, you know, depending, obviously you're in my class, but depending on who you have as your instructor, some instructors don't want you to use the solver. And, you know, that's their prerogative, that's fine, but I'm like, we've got these, right? If you've got it, you might as well use it. We can find the equilibrium constant for a weak acid from the pH of a weak acid solution. It's kind of working backwards, right? So this 0.175 molar weak acid solution has a pH of 3.25. Find Ka. I'm still going to make an ice table. Here we don't know what the weak acid is, because then we could, if we did, we could look it up. So H plus and A minus. Initial change, equilibrium. We're given the concentration of the acid, so 0.175. We're going to assume that the hydrogen ion concentration initially is 0 and that the conjugate base is 0. Now this is similar to problems where we calculated an equilibrium constant from equilibrium concentrations. If we know one equilibrium concentration, we can use our ice table and figure out what the other ones are, and then plug them into the equation. Ka is going to be equal to H plus times A minus divided by HA. What is that pH telling us? The hydrogen ion concentration. Hydrogen ion concentration equals 10 to the minus whatever the pH is, so minus 3.25. Zero point 0.0005623. That is the equilibrium concentration for hydrogen ion. We measured it using a pH meter. So I'm going to put that in for the equilibrium concentration of H plus. From that piece of information, I can find numerical values for the others. When this dissociates, when this ionizes, I'm going to get equal amounts of H plus and OH and A minus, right? So our change here is that this increased by 0.0005623. This also is increasing by 0.0005623. So my A minus concentration is also that, and my A minus my HA changes by what? Minus that. I'm going to call it 5.6 there because I ran out of space. questions? So I can figure out what 0.175 minus 0.0005623 is equal to. Point 17443. I'm not being religious about my significant figures, but I'm using them as a guide to avoid having to write down a crap load of digits. So I've got values there, right? So I can calculate Ka by plugging these numbers in. A minus and H plus are the same number. So that's just squared. And the HA concentration is 0.17443. I'm getting 1.8 times 10 to the minus 6. Any questions? Another thing we sometimes look at is the percent ionization of a weak acid. We said that a weak acid does not ionize completely. We can look at how much does it ionize. That would be the ratio of the ionized acid concentration to the initial acid concentration multiplied by 100. And that percent ionization is going to be relatively small for weak acids. For a strong acid, it'll be essentially 100%. Okay, so find the percent ionization of a 0.250 molar acetic acid solution at 25 degrees Celsius. Ka is 1.8 times 10 to the minus 5. So percent ionization that's what we're trying to find, and we need to know what bits of information do we need to calculate that before we just start calculating junk. So what we want here is we want the equilibrium concentration of the acetate ion. That's that conjugate base, divided by the initial concentration of the acid, times 100. Well, we've got the initial concentration. That's right there. We need to figure out what's that equilibrium concentration of the weak acid, of the conjugate base, sorry. Well, it is easier to write HA, and I had a little debate with myself. Well, the equation's right there, and then we're using it in here, and so I don't want to confuse anybody. But yeah, you can just call it A minus, and HA. So our initial concentration here is 0.250. We're saying that this is approximately 0, and that is 0. Change is minus x plus x and plus x. And equilibrium is 0.250 minus x, x, and x. We have our equilibrium constant there, acid dissociation constant, 1.8 times 10 to the minus 5. And that's going to equal x squared over 0.250 minus x. Because it's the concentration of hydrogen ion and the conjugate base, x times x, there's my x squared, divided by the concentration of this, which is 0.25 minus x. So you can probably guess I'm just going to use my solver because I like the solver. 0.25. X is 0.00211 molar. That is equal to the equilibrium acetate concentration. Now, X is small would work here because this is 0.8% of 0.25. So here's my concentration at equilibrium. So that's what I'm going to plug in here. 0.0021112 divided by the initial concentration, 0.250. These are both molarity, and the molarities cancel out, times 100. And so this is 0.84%. Acetic acid is only 0.84% ionized at this concentration. That's a very small amount. It's mostly acetic acid molecules. Any questions? So there are some trends that we can observe for weak acids. The equilibrium hydronium ion concentration is going to increase with increasing initial concentration. That should make sense. You put more acid in, you're going to get more hydronium ions. What doesn't really make sense is that the percent ionization of the weak acid decreases as you increase the concentration of the acid. We have an example here for nitrous acid at 0.2 molar. It's 4.8% ionized. At 2.5 molar, it's only 1.4% ionized. So obviously the question is why, and we need to consider this equilibrium. I think next page. Come on, next page. No. Okay, gotta stick with this page. What was I supposed to say here? Well, we're interested in the percent ionization, right? Well, let's just look at the second example there, where we've got 2.5 as our concentration, essentially 0 and 0, and then we've got minus x and plus x and plus x. And so 2.5 minus x, x and x. We end up with Ka, which we don't know here, is x squared over 2.5 minus x. When we calculate the percent ionization, that's going to be x over the 2.5 times 100. I'm really curious to see if this is going to go anywhere useful. To explain the trend in percent ionization, let's look at this generic equation for the ionization of a weak acid. And we're just going to throw some simple numbers in here. Let's say that at equilibrium, the concentrations of each of these are 1 molar. And so then we can find that the equilibrium constant must be 1 times 1 divided by 1, which of course is equal to 1. Now let's make this more concentrated. Let's start with, let's just make everything 2 molar and see what happens. So if we have 2 molar concentrations, now we've disturbed the equilibrium. What we're calculating here is going to be Q. And it's going to be 2 times 2 divided by 2. And that's going to equal 2. So what this tells me, Q being greater than K, tells me that this reaction then is going to shift. It's going to shift in the reverse direction towards more of the intact molecules forming less ionization. So that's one way to think about it. Let's look at mixtures of acids. So if we have 2 different acids mixed together and we're trying to calculate the pH, that could get complicated, right? Most of the time, we can actually neglect the weaker acid and just focus on the strong acid. The effect of the strong acid is much more important than the weak acid. So if we look at this mixture, here we have 0.1 molar HCl, which is a strong acid, and 0.1 molar formic acid, which is a weak acid. We have 3 sources of hydronium ions. We've got hydronium ions from the strong acid, hydronium ions from the weak acid, and from the autoionization of water. Are we okay with that? So here we have our strong acid, here we have our weak acid, and here we have the autoionization of water. The hydronium ions that are formed by the HCl suppress the formation of hydronium by the weak acid and by water. So this HCl ionizes completely. If we've got 0.1 molar, then we're going to have 0.1 molar H3O plus. This equilibrium that water sets up with itself, if I add a bunch of hydronium ions, what is that going to do to this equilibrium? It's going to cause it to shift to the left. That is suppressing the production of H3O plus by water. And it'll do the same thing to this equilibrium. Adding a bunch of H3O plus from that strong acid causes this equilibrium to shift to the left. So we can set this up as an ice table looking at the contribution of the weak acid. And so here's our weak acid, and it's going to ionize and form these ions. Here our initial is 0.1 for the weak acid. Now, instead of saying that the hydronium ion initial concentration is 0, or approximately 0, we're going to say it's 0.1. Why? Because we had 0.1 molar HCl. 0.1 molar HCl makes 0.1 molar hydronium ion. And there's no equilibrium there. It just goes. It's done. So that's our starting amount. And then our starting amount for the weak acid's conjugate base is 0. And then we go minus x, plus x, and plus x, and we end up with this. And we can calculate that. Here's our weak acid equilibrium constant. That's going to be 0.10 plus x times x divided by 0.10 minus x. And my solver is telling me that that's 0.000179. This is the contribution to the hydronium ion concentration from the weak acid. We could do similar calculation for the auto-ionization of water, but this being so much smaller, the X for that is going to be even smaller. 0.000179 divided by 0.1 times 100 is 0.18%. So the contribution from the weak acid is only 0.18%. We can ignore that. Concentration from the auto-ionization of water is even less. Any questions? So 3 sources. When we have two, now we're going to talk about 2 weak acids. We've got 3 sources still, each of the weak acids and the water itself. We can ignore the weaker acid in the water when the Ka's of those weak acids differ by more than a factor of several hundred, and the concentrations of the acids are similar, or the concentration of the stronger acid is greater. I know that's not a super easy list of things to remember. But this first one, the Ka's being different by more than a factor of several hundred, that's telling us that the stronger weak acid, its Ka is like 1,000, 10,000 times bigger. Then we can see that that equilibrium is going to have more effect than the weaker weak acid. And if the concentrations, if we have a high concentration of the stronger acid, that's going to have an even greater effect. Now, if the weaker acid is much higher in concentration, then we have to consider all of them. Okay, let's find the hypochlorite ion concentration of a mixture that's 0.3 molar HF and 0.1 molar HClO. So we have 2 weak acids here. The Ka for this one is 10 to the minus 4. The Ka for this one is 10 to the minus 8. That's a difference of 10 to the 4, or 10,000, right? So that's more than several hundred. So, and we've got our stronger acid here has a higher concentration than the weaker acid. And so we can probably ignore the hydrogen ion contribution from this acid. So we'll set up an ice table for the stronger weak acid. Initial is 0.300, and here we're saying this is approximately 0, and this is 0. Our change minus x plus x plus x, equilibrium 0.300 minus x, x and x. .9 times 10 to the minus 4 is the equilibrium constant. That's going to equal x squared over 0.300 minus x. Are you following me fairly easily on how I'm getting that? Yeah, I think we've done it enough times. Now, you could try x's small approximation, but again, why? Why bother? 6.9 times 10 to the minus 4 is equal to x squared divided by 0.3 minus x. And so x is equal to 0.0140. Because honestly, I can punch it into my calculator and solve it faster than I can use the X's small approximation. So this X is telling me that the contribution of H plus from the HF is a concentration of 0.014 molar. Now that's not telling me anything about the hypochlorite ion concentration. The hypochlorite ion concentration, we're going to have to figure out how much of that second weak acid ionizes. So now we're going to make a nice table for the weaker weak acid. So our initial is the initial concentration of that acid, 0.100. Now, instead of saying that the hydrogen ion concentration is initially essentially 0, we're going to look at the contribution from the stronger acid, because the stronger acid is putting out this. So I'm going to put that in there, 0.0140, and our concentration of hypochlorite is 0. Do you see why I put this number in there? So then we've got changes. We've got minus X, plus X, and X. Got an equilibrium expression here, 0.100 minus X, 0.0140 plus X, and X. The acid ionization constant here is 2.9 times 10 to the minus 8. And so that's equal to 0.0140 plus X times X divided by 0.100 minus X. This X here, what does that X represent? That's the equilibrium concentration of the hypochlorite ion, which is what we're trying to find. So 2.9 times 10 to the minus 8, 0.014 plus X times X divided by 0.1 minus X. That's pretty small. 1, 2, 3, 4, 5, 6, 7. So that's the concentration of the hypochlorite ion at equilibrium. That is also the amount that would be added to the hydrogen ion concentration from that stronger acid. If I take 0.014 and add 0.000002, does that matter? No. But if we're concerned about the hypochlorite ion concentration, is that concentration 0? No, it isn't. Any questions?